In this video, we will solve another interesting problem known as linear assignment. We will rephrase the problem as a network problem so that we can find the optimal solution using network flow optimizers. Okay, so let's look at the problem first. So we have four tasks, tasks 0, 1, 2 and 3, and then we have four workers, workers 0, 1, 2 and 3. Now we want to assign one task to each worker, okay? And here we see the amount they charge. For example, worker ID 0 charges $90 to do task 0. And then $76 to do task 1, $75 for task 2 and $70 for task 3, right? Similarly, for example, worker ID 3 charges $115 to solve task number 3, right? So how do we assign these tasks, these four tasks to these four workers so that our expenses are minimum? Okay, that's the problem. Now in this part of the code, I just copy the table from the document. So it is copied as a string, and just we are parsing this string to make it into a data frame. Okay, so don't worry about this code. All right, so let's say we are simply assigning the first task to first worker, second task to second worker, third task to third worker, fourth task to fourth worker. So the cost would be $90 plus 85 plus 90 plus 115. Okay, so it would cost us $380. But is there a better way to assign these tasks to these workers so that we can pay less than $380? Okay, so that's the question. All right. So just representing the problem as a network. So here we have four workers, and similarly we have four tasks. Now each worker can solve all four tasks, right? But it might be the case that, let's say the worker 1, he may not be, or he or she may not be able to solve, let's say task 1. So in that case, we would have NA, or and also we would not have arc connecting these two nodes. Okay, so just for a moment, ignore these red lines. Just imagine them as the purple lines. Okay, so from every worker node, we have connection to every task node, right? 4 nodes. Now we want to solve this problem using network flows. But we know for network flows, optimizers, we need a source and sink, right? So what we do is we add a fictitious source and a fictitious sink, okay? And then we are reindexing the nodes so that our source node is 0, our worker nodes are 1, 2, 3, 4, our task nodes are 5, 6, 7, 8, and then our sink node is 9, okay? So we started source, and our 4 workers are equally probable, so we don't have any constraints on going from node 0 to node 1, okay? And similarly, from tasks 5, 6, 7 to sync, all are equally probable, or there are no constraints, right? Because the source node and the sink node, these are just fictitious nodes needed to phrase the problem as a network problem, okay? All right. This is a problem we solved in the previous video where we have on each route or arc, we have a capacity constraint as well as we have the cost associated with it. Okay. So in our case, we have the cost associated, but we do not have any capacity constraint, right? So along each arc, the capacity is equal, right? We can take it as 1 or 2 or whatever, but let's take, by default, we take it as 1. So all arcs have equal capacity. All right. So in order to construct the network, we are going to translate this diagram into NumPy arrays. So we will be creating 4 arrays. So first the start node and then the end nodes. Now, as we can see, from start node 0, we can go to node 1, 2, 3, 4. right? So that's what we see here. So from 0, we can go to 1. From 0, we can go to 2, we can go to 3, we can go to 4, right? Now these, so for example, here you will see one list, here you will see another list, and then another list. It need not be like that. This is just so that we can visualize it easily. But this whole thing is a single list, okay? All right. And then, for example, from node 1, we can go to node 5, 6, 7, 8. Okay. So, for example, here you will see from node 1, we can go to 5, 6, 7, 8. All right. And similarly, from, for example, let's say node 5, we can only go to node 9. So that's what you see here. From node 5, we can only go to node 5. Okay. So that's how we have constructed the arcs, or the pair of nodes. And then the capacities. So as we just discussed, the capacity is equal along every arc. So let's just take that as 1. Okay. So the capacity is 1 for any arc in this network. And then finally, we have the cost associated. Now, to go from node 0 to node 1, we don't have any cost, right? Because only the workers are charging here. So the cost from 0 to 1, 0 to 2, 0 to 3 and 4, for those 4 nodes, the cost is all 0. And similarly, the cost from the task to sync node is also 0. So these 4 nodes also, the arcs, the cost is 0. And this is where we have the actual worker costs. So worker 1 to solve task 1 or node 5 is charging $90. And then for task 2, which is known as task 1, just don't get confused with that index. So charge 76 for the third task, 75, and for the final task, $70, right? So that's what we are seeing here. So 90, 76, 70, 75. All right. So we simply translated this network into 4 lists or NumPy arrays. All right. Then, as I mentioned here before, so this we created in the form of 3 lists just for easy visualization, but it is a single list. Okay, single list like this. All right. Then we define our source and sink. So the source is node 0, sink is node 9, and the number of tasks we have are 4. So the supplies, so here we start with 4 tasks, and at the sink, we want to accomplish all the 4 tasks, right? And we do not have anything in between, right? So our supplies will be the number of tasks, 0 at all the remaining 8 nodes, and at the sink, we want to conserve it so that we want to finish all 4 tasks, right? So we have defined the supplies. And then once we are able to define the problem in this manner, 50% of the work is already done, right? So then we are simply importing this min cost flow as in the previous video, and then we are instantiating, okay? And then we need to add the network to the optimizer, right? So basically these 4 arrays. So in a previous video, what we did is we have used add arcs. So notice the plural. We have used add arcs with capacity and unit cost, right? Where we have supplied the lists are NumPy arrays at once, right? Here there is another way to do in case if you need to do add one by one for some reason. Let's say some network is evolving over time or something like that. You can do the same, right? So instead of arcs, we just use arc, and then we add each arc one at a time, right? For example, so first we are adding, let's say this arc. So this one, 0 to 1, the capacity is 1 and the cost is 0. Okay, so that's what we are adding. So this would be 0 node, this would be node number 1, and then the capacity is 1, the cost is 0. Okay, so these 4 elements, 0, 1, 1, 0. All right, so we add the network to the optimizer, and then we need to provide the supplies, right? Again, similarly, we are looping over the supplies, which is simply at the source, we have n tasks. At the sink, we want to complete n tasks, right? So we have supplied the tasks as well. And then we have defined the problem, defined the constraints and everything. Now we do this this cast flow between node 0 to node 10, right? Source and sink. So we simply solve it. And if the status is optimal, which means we are able to find optimal solution. Okay. So yeah, here we are printing the total cost. And then for each arc, we are processing the steps are the solution, right? Okay. So what this is just easy to read. I mean, nothing happening here. Once we solve it, we'll have the cost in this variable, optimal cost. And then in the flow variable, we can see how the tasks are distributed. Okay. So the solution is saying, hey, assign task number 8 to worker 1. Now here the indexing is starting from 1, whereas in the data frame, the index start from 0. So let's see. So worker 1 means actually this worker, and task 8, which means task 8, which is the last one. Okay. So what the optimizer is saying is, hey, to this worker, apply or assign this task, and that would cost us $70. Okay. And then to the second worker, assign task number 7, and that would cost us $55, right? And similarly to the third worker, we are assigning the third task, which is $95. And finally, for the last worker, we are assigning the very first task, which is costing us $45. So sum of all these is $265. Whereas our initial assignment, which is just assigning task 1 to worker 1, task 2 to worker 2, so on and so forth, has resulted in a $380 cost. Whereas if we go by the solution provided by the optimizer, it's going to cost us only $265. Okay. All right. So that's a good solution. So, and that's the minimum for this problem, right? So in this tutorial, we have solved a linear assignment, right? The reason it is called a linear assignment is because we are assigning these tasks linearly to the workers, right? So we have rephrased the problem as a network problem, so that we used this network flow optimizer to find the minimum cost to get the work done. That's all for this video. Thank you very much.